Okay, so in our previous discussion, the adjoint goes from G to, invertible matrices of D by D, invertible matrices over R. It was seen to contain only Lie algebra isomorphisms. In other words, for each G in G, we saw that the adjoint of G goes from frac G to frac G was a Lie automorphism of G. In other words, an automorphism, a Lie automorphism is a isomorphism from G to itself. All right. Something neat happens if G happens to be a subgroup of the orthogonal or unitary or symplectic matrices. In fact, the adjoint mapping ends up being it's norm preserving. The length, the standard length with respect to is induced from the standard inner product on O and K, right? That norm, it's preserved under the adjoint mapping. Right, so that's pretty neat. The proof is given on page 122. Corollary: if the fixed basis beta of G is orthonormal with respect to the the inner product, then I don't know if that's supposed to be an R or K. Sometimes we give theorems just for R here and there. Reals are special. Let me look that up real quick. By the way, if you're studying TAP seriously, you should make sure to look up the errata for this book. There's like a 2-page list. There's not too much, and you can usually see them because his writing is very clear. But it's probably a good idea to print that out and keep it with you, right? It's a little late for me to tell you that, I suppose. All right. Anyway, corollary. Nope, that's the reals. That's not a typo, or at least it's the same as TAP has. Let's see here. With respect to the inner product on R, then the adjoint G is an element of the orthogonal transformations of D, D by D for all G and G. So in other words, the adjoint going from G to OD is a homomorphism into the orthogonal group. So fixed basis beta, if it's orthonormal with respect to the real inner product, then the adjoint is an orthogonal transformation, and so that means, and that's for each G, so the big add is always assigning something in here, so it can be basically a mapping from G to OD. Cool. What was G here again? G was a what? It's a matrix group, right? So if we pick a basis for the Lie algebra, which is orthonormal, then we get a representation of the group inside the orthogonal matrices. Pretty. So I think the thing I was just talking about, 120 to 121, is an example of this in action, where he has the adjoint G. His choice of G there is actually SO3, and SO3 represents itself. Of course, SO3 is a subset of O3. Proposition 8.14: if G is a subgroup of the n by n orthogonal transformations over K, then for all x, y, and z in the Lie algebra, we have that the, let's see here, the bracket xy with z is equal to minus the bracket xz with y. So if we trade the z and the y here, see that? They traded places, then we generate a minus like that. And that's the real inner product. All right, moving along here. Some global conclusions. If G is a path-connected matrix group, all right, and H is a subset of G, is a path-connected, if that's a path-connected subgroup, then the Lie algebra of G, suppose the Lie algebra of G is frac G, and the Lie algebra of H is frac H, then H is a normal subgroup of G, all right? Remember, normal subgroup means that the factor group is itself a group. Anyway, normal subgroup is basically the, well, you'd like to call them ideal subgroups, but the term normal is, we're stuck with it. So a normal subgroup of G, if and only if the Lie algebra H is an ideal of G. Here the ideal means that it's, of course it's closed under itself because it's a Lie algebra, but it's also, if you take the bracket of something in H with something in G, you're back in H again. So one of my fellow professors calls it uber closure. Anyway, the Lie correspondence. So that's basically saying ideals at the level of the algebras connect to ideals at the level of the group. That's, subject to this mild topological condition that we're talking about path-connected group and a path-connected subgroup. All right. Otherwise, you can have some kind of like, well, get to it eventually. The Lie correspondence theorem. There is a natural one-to-one correspondence between subalgebras of GL and R and path-connected subgroups of GL and R. So there you have it. If you can, classify subalgebras of this, that gives you a good picture of what are the possible path-connected subgroups of that, which is pretty cool because you like to trade problems that aren't in algebra for problems in algebra usually. Now, there's also a really nice discussion of what's called a double cover. Much more details in TAP than I'm giving you here. But just to say a word or two about what is a double cover is a mapping from, it's a homomorphism, right? From one group to another that is locally a diffeomorphism, but globally not. So globally it's a 2-to-1 map, all right? So these are the so-called double covers. SP1 cross, well, first of all, SP1 is the double cover of SO3. SP1 direct product SP1 is the double cover of SO4. The symplectic group of order 2 is the double cover of SO5. Special unitary matrices of order 4 is the double cover of SO6. And so generically speaking, well, the mapping here, by the way, is given by the adjoint, which is kind of cool. So generally, the double cover of SON is called spin N, the so-called spin group. And that does have connection to, like, maybe you've heard of spinners in physics. But anyway, that is a story for another day. That brings us to Chapter 9. Woohoo! All right. So I'm going to start and stop again here.